Hey everyone, this is Yusuf, the Circuits TA, and today I'll be going over the topic of Thevenin equivalent circuits. On this first page, I'm going to do a brief intro on Thevenin and what it is and how we will use it in our class. So Thevenin is a simplification process that works with any linear circuit. So it's similar to reduce and return and nodal analysis, where it's a way we can look at our circuit, a way we can analyze our circuit, and get certain bits and pieces of information from it. And the last part from this first sentence, any linear circuit means we must have ohmic components. We must have our resistors, our inductors, our capacitor, anything that behaves similar to that type of response. If we have a diode or if we have something else, a non-ohmic conductor, things will get a little bit more difficult and Thevenin will not work. In this course, Thevenin will always be a pretty good option. As long as we're not working with diodes, we mostly stick to those ohmic components. The next sentence about Thevenin is, it's great at isolating a single point or part of the circuit. A lot of times in Thevenin, they will ask us about a specific load, whether that's the load resistor, load inductor, or unknown load component. And we want to know what is the voltage going to this load component, or what's the resistance seen by this load component. And this also allows us to change our load. So if we want our load to be a variable, Thevenin allows us to easily do that. We can simplify the rest of our circuit by taking out our load variable. And then when we need to, if we wanted it to be 20 ohms, we can keep our new simplified circuit and use 20 ohms. If we now want to use 50 ohms for our load variable, we could use 50 ohms using that same equivalent circuit. Before we go too deep into the solving process of Thevenin, one important thing to know is that it is not an all-powerful technique. It is not a one-and-done technique. When I start my Thevenin process, I still have to think about all those analysis skills that I learned in the past, about looking at open circuits, about looking at short circuits, or even nodal analysis, voltage divider, or anything like that to get to the final values I want to find. If we scroll down, this will be the circuit we're working on. It is from chapter 9. It is problem 16a. And in this circuit, before we get started, I'm just going to label what we have. We have one 20-volt battery, and then we have a total of 6 resistors, R1 all the way to R5, and then we also have our R load. The question was asking us to find the Thevenin equivalent circuit. So already on the bottom here, I drew what we should expect the Thevenin equivalent circuit to look like. V Thevenin for our one voltage source, R Thevenin for one resistor component. And in the Thevenin process, that is our main goal. We want to go from a more complicated circuit like this top part and get to one circuit with one voltage source and one resistor in series. If the question asks further, at the end is where we would connect our load and then go off based off values off that. In this case, since they're not going to ask any questions on our load, we know our final answer should look like this. In the Thevenin process, there are 2 steps. They can be done in any order. There is the Thevenin resistance, RTH, which was on our previous slide. And then there's VTH, our Thevenin voltage. You can start at either or you want. They are 2 different circuits. So it is important to not mix and match the 2 values from the circuits. So on this first slide, I have my original circuit and the things we talked about for the intro. Here, I'll have my resistance circuit. And on the third slide, I'll have my Thevenin voltage circuit. And all of them will be slightly different and have their own values attached to it. Starting on this first circuit, I'm just going to go through the certain steps I've already written down for me to go through. First step says remove the load component. In this case, it's our resistor, or R load, and mark terminals A and B. So I'm going to go ahead and get my eraser. I'm going to remove R load. And I'm going to mark my terminals A and B. This is a perfectly fine representation of that. If you wanted it to go down a little bit more and have something like that, that also still works as long as we have the same idea. This second step is telling me to turn off or remove all voltage and current sources. From our analysis on the first page, we know there's only one voltage source. So I'm looking at this 20-volt battery and I want to get rid of it. And when we're working with this Thevenin resistance, we can think about what we've done practically in the lab. Whenever we measure resistance on our proto boards or in our circuits, we always have no voltage being provided to our circuit because we don't want that to mess with the reading. So if we want 0 volts across something, we know that this should be a short circuit or just a straight wire. So I'm going to go ahead and remove my battery. And this blue line is going to represent that short. In this case, this short will not change anything in my circuit besides removing my voltage source. This wire replacement is not shorting out anything in my circuit. And we will see that when I go to draw my current arrows, okay? So my first 2 steps are done. And this relates back to what I was saying earlier, that Thevenin is not a one and done method. I've now done my Thevenin steps, but now I need to remember about what I know about circuits, circuit analysis, current directions to find the value I want to find. So this total resistance seen from the load is going to be my RTH. So one way to think about it is I can connect an ohm meter right in between terminals A and B, or I can also draw a very large arrow. That's a method I like to do as well, going into A and B. And this A and B, this arrow, is really showing me the perspective of the load. So a lot of times we didn't say it, but it's just assumed when we have our original circuit, when we find the total resistance, it's from the perspective of the source. Here, we want the perspective of the load, so that's why we removed it, and now we're going in from that direction. So I'm going to start by drawing off my current arrows. I'm going to leave from this positive terminal. I'm going through R5, going right to left. I'm going to go down R4, and my current is still going to split across R3. I'm going to keep going through my circuit. Current's going to go down R2, go across R1, and go down where my battery previously was. And now with these current arrows, I know a little bit more about my circuit. At first glance, this could be a little overwhelming. I do have a lot of information on my circuit. I have a lot of current arrows. And so I want to think about what can I simplify first. In this case, since I know that current is splitting in my circuit, I know that this is not just one series or one parallel circuit. And I need to look at what is connected to 2 terminals to see what's in parallel and what is sharing the same current to see what is in series with each other. Immediately in my mind, I don't see anything in series with each other. I'm going to go ahead and start at the most left side of my circuit. So I'm going to start right here. And if I mark this as terminal C, and if this was my ground node, this bottom portion, or my B node, whatever I want to call it, I can see that both R1 and R2 connect from C to B or C to our ground node. So another representation of this is a circuit just like that. And so this tells me that R1 and R2 are in parallel with each other. So I can go ahead and do that and simplify my circuit on that side. So if I did my equation, 1 over 5 plus 1 over 20, all raised to -1, I will get 4 ohms. I'm going to scroll down again. I'm now going to redraw my circuit one more time in this case. I now have this 4 ohm resistor in place of where the 2 resistors were. And this is, I can call this RP. And then, just like before, R1 and R2 are no longer here. That's what I just combined. R3, and then R5. So the same idea I have here, I simplified my circuit, and I want to make sure I find my final answer whenever I'm going for my resistance Thevenin. So now here I see, if I put my values back on my circuit, R3 had 12 ohms, R4 had 16 ohms, and R5 had 2 ohms. If I'm drawing my current arrows again, same idea, going from the perspective of the load, I'm going up, I go down across R4, I go through R3, and I go through R parallel. R3 and R parallel actually have the same current. This current 1 and 2 are equal to each other. They are in series with each other. So I can add R3 and R4 together. So I'm doing 4 ohms plus 12 ohms. And this will get me 16 ohms. And now I have something that I'm more used to seeing. Now I have 3 resistors total. My R4 and my new RX, I can call it, is in parallel with my 16 ohms. And then I have this final R5, which I know is going to be in series with a combination of. So I'm thinking here that this RX and R4 are in parallel. 1 over 16 plus 1 over 16th raised to -1. I know this will be half. I'll have 8 ohms as my final resistance. And to fully simplify my circuit, I have 8 ohms for all my resistors simplified. So this is really resistors 1 through 4 after completely combining all of them. And this is my last resistor, resistor 5 at 2 ohms. My resistance comes out to a total of 10 ohms. So this is my R Thevenin at 10 ohms. I can go back to my previous work on this. And now I'm going to write 10 ohms as my R Thevenin. Key parts about this process is remembering that I'm looking at the perspective of the load, and I remove my current and voltage sources. Okay? And now that I've finished my R Thevenin process, once again, my other process, my V Thevenin process, is separate from it. So I have my same circuit again. I copy and pasted it from the previous slide, but I'm going to have to modify it before I do any analysis or solving on here. So a couple quick notes. I want to mark the terminals A and B, and I want to remove the load, leaving it as an open circuit, similar to what I've done before. I'm removing my load. Okay. I'm marking terminals A and B, and VAB will equal my V Thevenin. Okay, I did the first step. Next step is telling me find the open circuit nodal voltage, and then this can be using nodal analysis, KVL, voltage divider, reduce from return, any method you would like. In this problem, we're going to go with nodal analysis. Before we move on, I'm going to talk a little bit more about what this means, open circuit nodal voltage. So in our circuit, this first step, we removed our load and we are leaving it as an open circuit. So this part right here is an open circuit, and this tells me about the current. So the current in my circuit, if I start all the way back at my battery, I can have it going through R1 after leaving the battery. I can have it going down R2, go and get over R3, and down R4. I am not going to have any current at R5, and that is because of this open circuit I made at A and B. So R5 is a hanging resistor. Hanging resistors do not add any resistance to the circuit, and there's no current across it. So when I'm looking at VAB, I'm going to redefine VAB as the voltage across VR4. So my open circuit nodal voltage is VR4, it is VThevenin, it is VAB. And this is something you can always do. Whenever I define VAB as VThevenin, I can find something in my circuit to redefine it as. In this case, VR4, you have multiple ways of doing it. I could simplify my circuit a little bit more and get to a point where I can see different values and then return those values back up to my original circuit. So this would be that reduce and return method. Here, I am going to use nodal analysis. And if you're unfamiliar with nodal analysis, it is looking at KCL and saying the total currents in equals the total currents out. And this is at a singular node. Okay? And then I'm going to model those current directions. I'm going to draw these current directions in green and also purple respectively. So before we get started, we're going to look at our unknown nodes and see what we need to find. I see one node here. This is the 20 volt battery connecting to wire, and ground is at the bottom here. So I know this is 20 volts. I have an unknown node here. A and B is already used, so I'm going to go ahead and just call this node C. And then I have one more node right here. I can call this node VD. And this ground node, I know it's all connected to the ground, so this is all going to be 0 volts, okay? So if I start at VC, I'm thinking about total currents in equals total currents out at a node. So VC, I have 1, 2, 3 components. So I'm going to have 3 arrows and 3 currents in my equation. So I have one going in, I'll have one going out, and I'll have another one going out across R3. So if I was to write this, I would say 20 volts minus VC over my 20 ohms. That's my current going in. And then my 2 currents going out. Remember, this is the summation symbol. So I'm going to add those 2. So one of my currents out is going VC to ground over the 5 ohms. My other one is going VC minus VD. So I'm going from VC to VD over my 12 ohms. Now I'm going to switch over to the darker purple. And this is going to be my equation for VD. In this case, because of that hanging resistor and because there's no current through R5, I'm just going to have 2 arrows, one for R4, one for R3. So 2 currents in my equation. I'm going to still have VC going to VD over the 12 ohms. And then I'm going to set that equal to the current going out. And that will be VD minus 0 over the 16 ohms. And then, so I can solve this system of equations using substitution, using elimination, or what other method I want to. In our class, we're using our TI inspires. So make sure you know how to put in the system of equations to our inspires. Once you set up this equation correctly, the answers you should get is VD equals 3.5 volts. And VC VC should be equal to 3.5 volts. I switched them up, so sorry. 3.5 volts, and VD is going to be 2 volts. Okay? I can scroll up. In my circuit, I can see where this VD is. The 2 volts right here is right above R4. So from R4 to ground, I drop 2 volts across R4. So VD is equal to the voltage drop across R4 because I'm going to ground. So now I have found my VThevenin process. So I'm once again going to go back to my final circuit. I'm going to write in 2 volts for Thevenin, and I can circle this, and this will be my final Thevenin equivalent circuit. Thank you.